Hello, my name is James Smith. I am from the University of Portsmouth in the United Kingdom. This paper, published in Applied Surface Science, concerns the friction and adhesion mapping of the substructures of the human hair cuticle using the atomic force microscope. The structure of the human hair cuticle is complex. Each consists of three main layers, the endocuticle, the exocuticle and the A layer, which contain increasing amounts of cysteine and hence possess higher degrees of cross-linking. Cuticles are separated by a cuticular cell membrane complex, which consists of a polysaccharidic layer, labelled delta, sandwiched by inner and outer layers, labelled beta. The outer beta layer, largely present on the outer surface of the cuticle, contains an unusual branch-chain carboxylic acid, known as 18-MEA. This layer is thought to give hair its low frictional properties and the associated ease of brushing and combing. 18-MEA may be removed by excessive grooming, by treatments, or by aging, and is of interest to the toiletry and cosmetic industries. In collaboration with scientists from Tokyo and Portsmouth, we have developed a method for mapping local variations in friction coefficient of surfaces using the AFM. The novelty of our approach is that the friction coefficients have been determined quantitatively from Amonton's law of friction, which relates measured frictional forces to the applied load. To effect this, we scan the same area using 5 different applied loads. The friction coefficient and force of adhesion were then extracted from the AFM data and both properties mapped. The calibration method using diffraction gratings of known blaze angle was employed. On the left, a topography image of the surface of a human hair is shown. We have used left-shaded images to enhance the contrast. We have also reduced some of the scatter in the friction data by averaging values from surrounding pixels. This reduced resolution, although the image quality was not significantly affected. From the shaded topography images, we could identify areas that corresponded to different surface-exposed substructures from which frictional force data could be extracted. By boxing around selected areas, the influence of scale edges on friction could be avoided. The Amonton plots were linear for all the substructures, even for the rough endocuticle that is known to consist of cell remnants. Quantitative friction and adhesion maps were extracted from the AFM data. A shows the topography image, B and C show the friction maps, taking into account different range limits. D shows a derivative map of the friction coefficient, which we named a mu acceptance score that gave a useful indicator of local variation of friction coefficient. E and F show adhesion maps, again with certain range limits. The smooth outer beta layers, containing 18-MEA, all had similar low values of friction coefficient, reflecting their known homogeneity. Some of the newly formed layers were of lower friction than the outer beta layers, possibly due to less weathering and/or reduced roughness. Endocuticle areas had the highest friction coefficient, consistent with their granular nature. Force of adhesion maps, however, were less precise and less informative. They did not follow the pattern seen in the friction coefficient maps. In conclusion, we were able to produce quantitative friction coefficient and adhesion maps of the surfaces of human hair cuticles. With an uncoated AFM tip, friction coefficient maps showed variations in contrast, reflecting known surface chemistry and/or roughness differences between substructures. The adhesion maps were, however, less informative.